Hi everyone, I'm Alena Osipova, a customer engineer.
And I'm Wan Qiang, also a customer engineer.
And we both work here at Google Cloud.
Welcome to the Technical Series for Startups, where we are creating a series of videos for technical enablement to help startups to start, build, and grow their businesses successfully and sustainably on Google Cloud. In our previous video, we learned how you can innovate with machine learning solutions such as Contact Center AI and Document AI. They are prepackaged solutions designed for common use cases. Companies can start using them without relying on AI experts. However, if you start implementing custom solutions with AI experts in your team, you will start to face new challenges. And today, we are going to deep dive a little bit more into how you can implement machine learning ops on Google Cloud. We'll start by looking at some of the challenges that startups face when it comes to their machine learning workloads. Following that, we will introduce the concept of MLOps and how MLOps can be achieved on Google Cloud. We'll then walk through a demo of MLOps with Vertex AI in the Google Cloud console. And finally, we will learn about one of our customers and their MLOps journey.
Let's explore common challenges our customers are facing when dealing with ML workloads. Let's imagine that we are working with an advanced startup company with AI and ML technical skills. Employees have experience with frameworks, TensorFlow or PyTorch, and even were able to deploy their models on one of our compute options that we covered in the previous session, Cloud Run or Google Kubernetes Engine. The common challenges this company could potentially face include models don't make into production, high degree of manual and one-off work, no reusable or reproducible components, and many others. Further, we are going to explore how Vertex AI pipelines can help our customers to overcome those challenges. Why are ML workloads becoming so challenging to handle over time? Is that all because of the complexity of the code? In reality, only a small fraction of real-world ML system is composed of ML code, as shown by the small blue box in the middle. The required surrounding infrastructure is vast and complex.
Given all the challenges that comes with managing machine learning workloads, how can we best address them and help eliminate the management overhead that comes with these machine learning workloads? Here, we want to introduce the concept of MLOps. But what exactly is MLOps? Just by looking at the name, we can guess that MLOps is related to DevOps to a certain extent. We can define it as an ML engineering culture and practice that aims at unifying ML system development and ML system operations. In other words, MLOps aims to prepare infrastructure to streamline the production process of ML systems, such as training, testing, deployment, and monitoring. Most importantly, it is to ensure that the process is consistent, scalable, and repeatable. Within MLOps, there are multiple stages involved, and it often goes in this sequence. First, you start with your ML model development. Once you have decided on your model, you will have to operationalize your training by building a training pipeline. This includes gathering training data, running your training jobs, and evaluating the performance of your model. When your pipeline is up and running, you can conduct continuous training whenever there is fresh data or based on any custom metric that you set. The next step would be to deploy your model to a serving environment and prepare your model to serve predictions. As your model is in production and serving clients in real time, you will need to continuously monitor your model for any data drift or performance degradation so that you can intervene when needed. Finally, at the core is data and model management, which is essential to governing ML artifacts to ensure auditability, traceability, and compliance. At the same time, these can also be used to promote shareability, reusability, and discoverability of ML assets. To get started with MLOps on Google Cloud, we have Vertex AI. Vertex AI is Google Cloud's unified machine learning platform that allows you to create, deploy, and manage models over time and at scale. It is built on top of Google's robust and secure foundation and provides flexibility for users of all ML expertise, whether you are new to the domain or an ML expert. Imagine that we have done our exploratory analysis and built out our model in our Jupyter notebook. We are now ready to operationalize and productionalize our machine learning workflow. So what can we do to automate the process of extracting and preparing data, as well as training and deploying our model? To do so, we have Vertex AI pipelines that can help you automate the end-to-end process, allowing for repeatability and scalability when it comes to building your machine learning models. With pipelines, you can easily retrain your models at regular schedules based on new data that comes in without having to worry about infrastructure or management overhead. If you are interested in learning more about building your own pipelines with Vertex AI pipelines, do check out the link in the description box for a more detailed video under the AI Simplified playlist. Before you can start serving predictions to your end users, you will have to deploy your trained model to an endpoint for your users to access. For this, we have Vertex AI Prediction that can handle both online endpoints as well as batch prediction requests. With Vertex AI Prediction, you can deploy models trained with either AutoML or custom code to serve online and batch prediction requests depending on your use case. As Vertex AI Prediction scales automatically based on traffic, it extracts away any form of infrastructure overhead from the machine learning developers. On top of that, you will be able to split traffic between models and also customize the endpoint machine types based on your model needs.
Now let's move to the managing and tracking the model quality. What is model monitoring and what challenges does it help to solve? Model monitoring helps data scientists and machine learning engineer to answer the question, why does a deployed model perform in a certain way? Modern applications rely on a well-established set of capabilities to monitor the health of their services. Examples include software versioning, rigorous deployment processes, event logging, alert and notification of situations requiring intervention, on-demand and automated diagnostic tracing, automated performance and functional testing. Vertex AI provides a host of products to monitor and govern your models, all of which helps drive both successful and responsible AI deployment. Those services include monitor signals for model predictive performance and alert when those signals deviate, diagnose to identify the cause of deviation, model updating to trigger model retraining pipeline, integration with feature store. Model monitoring is only one piece of the MLOps puzzle. I would like to explain a bit more about training servant queue and data-driven detection. It helps to answer the following questions. Why does a model perform differently from the training time in the production environment? This is called training servant queue. This queue can be caused by a discrepancy between how you handle data in the training and servant pipelines, a change in the data between when you train and when you serve, and many other reasons. Among them, data drift is one of the common causes of this queue. Data drift is defined as variation in the production data from the data that was used to test and validate the model before deploying it into production. So you have to monitor how significantly service requests are evolving over time. This is called drift detection. So now, how do you manage and govern your ML models? Here are some products that you might find helpful. First up, we have a feature store that allows you to share and reuse ML features across use cases, allowing you to serve ML features at scale with low latency. On top of that, Google Cloud also offers ML metadata, which enables you to automatically track inputs and outputs to all your components. With this, you will be able to visualize, analyze, and compare detailed ML lineage. Lastly, Model Registry is a central repository where you can manage the lifecycle of your ML models. From the registry, you can have an overview of your models, so you can better organize, track, and train new versions of your model. When you have model versions that you would like to deploy, you can simply assign it to an endpoint directly from the repository to deploy it. Explainable AI is fully managed service on the Vertex AI that enables users to generate what are called feature attributions or feature importance values for their model's predictions. Feature attributions are an explainability method that shows users how much each input feature contributed to their model's predictions and to the model's overall predictive power. Explainable AI is built into multiple Vertex AI services. Users can currently get feature attributions in Vertex Prediction, AutoML Tables, and Vertex Notebooks. As a fully managed service, XAI is flexible, fast, and scalable. You can use XAI on models trained on tabular, image, or text data. It works on models trained using any ML frameworks, not just TensorFlow, and we support both online and batch prediction use cases. Explainable AI provides insights to improve the quality of the models. By refining the training data, you can identify mislabeled examples, active learning, misclassification analysis, and providing decision support to your stakeholders. On top of that, XAI supports tabular, image, text data from any TensorFlow model, fully managed, serverless, and fast to query. Let's explore on how to manage and govern a model in the next slide. I hope the above presentation helped you to understand more about MLOps, and now I would like to show you them in action. For this example, we are going to run a simple pipeline to train ML model, but please remember that it's not only for training. With Vertex AI pipeline, it's also possible to automate the entire lifecycle of ML models, such as training, testing, deploying, and monitoring. Vertex pipelines. Before creating the pipeline, make sure that necessary APIs are activated and Google Cloud Storage bucket created. To create a cloud storage bucket, click the Create button in the Cloud Storage dashboard. First of all, let's create a cloud storage bucket. Go to the navigation menu, then Cloud Storage, and click Create. Name your bucket and choose where to store the data, regional or multi-regional. Let's create a multi-regional bucket. The bucket is going to contain data, pipeline model, and serving model. After creating a bucket, make sure that Vertex AI API is enabled and necessary permissions are granted to your account to run the pipeline. Let's move on to the Vertex AI dashboard. Let's create a user-managed notebook. From Vertex AI dashboard, go to Workbench. From the code repo, I have an option to deploy on Vertex AI Workbench, and that's what I am going to do. After initiating the process, I can see user-managed notebook has been created with TensorFlow 2.8 environment pre-installed. You can do the same manually from the console and then upload your notebook with the pipeline code. Next, let's open Jupyter Lab and execute the code. The current pipeline defined using Python APIs. The pipeline consists of three components: CSV example gen, trainer, and pusher. Let's take a look at the pipeline's function. Example gen component brings data to the pipeline. Trainer component uses user-provided Python function that trains a model. Pusher component pushes the model to a file system destination. Then we define a runner to run the pipeline. And finally, submit the job. After the job runs successfully, let's explore the visual output. We can see our pipeline components. Let's select the CSV gen component and go to the node info. Here we can see our input parameters and our output parameters. The current pipeline is a good simulation of the production-like pipeline. In the pipeline, you can also define function-based or container-based components. Google also provides predefined pipeline components that you can reuse for your pipeline. When you deploy the pipeline, I would encourage you to check if components you are looking for already exist. For more information, please follow the link in the description. Next part is artifacts. Artifacts pass complex data, like training data, between components. Let's expand one of the artifacts. As we can see, it's no more than a path to our previous created cloud storage bucket. You can monitor each component CPU utilization from the pipeline UI by selecting Component and go to View Job. There are a few metrics you can see: CPU, GPU, and network that have been sent and received by each component. Those metrics could be leveraged to further optimize your workload on the component level.
Now that we have our trained model, let's import it into Vertex AI Model Registry, a central repository where we can manage the lifecycle of our ML model. To do so, head over to Model Registry and click on Import. Select Import as New Model. Alternatively, if you have trained a new version of an existing model, you can also choose to import as new version. Give the model a name, a description, and select a region. Since my model is trained with TensorFlow 2.8, I will select Import Model Artifacts into a new pre-built container, and then choose the corresponding model framework and version for my container. Next, you will need to specify the cloud storage directory that contains your savemodel.pb file. You can set up explainable AI here, but we'll skip this for now and carry on to import the model. So with our model in Model Registry now, we are ready to deploy it to an endpoint and start serving predictions. Let's head over to Endpoints and click on Create Endpoint. Give your endpoint a name. You'll be able to select either Standard Access Mode, which makes the endpoint available through REST API, or Private Access Mode, which uses a VPC network to create a private connection to the endpoint. I'll want to be able to access it through a REST API, so I'll select Standard. Here, we will select our model that we imported. If we have multiple versions of our model, we can deploy them to one endpoint and split the traffic between the different versions. Suppose you found a way to increase the accuracy of your current model with new training data. You can add the new model to the same endpoint to serve a small percentage of traffic and gradually increase the traffic split to the new model to 100%. But since I only have one version, I will leave the traffic split at 100%. Next, we select the compute resources to serve prediction traffic. I'll leave the minimum number of nodes at the default 1. Next, select the appropriate machine type and the service account. In the next section, we can set up model monitoring to monitor the performance of our models as it starts to serve prediction traffic. We will name the monitoring job for easy identification. Set how frequently we want the job to run. I'll leave it as the default at 24 hours. We can also set the monitoring data window, which determines the length of the window to pull prediction traffic from. I'll leave it blank so that it will default to the monitoring interval. Next, we can set up alerting so that relevant stakeholders can be notified when a model exceeds the alerting threshold. Lastly, we specify a sampling rate of 10%, which is the percentage of prediction requests within the monitoring window that we want to sample. For the monitoring objective, we can choose to either detect training serving skew or prediction drift. So for demo purposes, I will select training serving skew. We will need to provide our training data so that the monitoring job can compare. Then we specify the target column name. I'll leave the alert threshold as default, so it will be 0.3. Finally, we'll click on Create, and we will see that the status is shown as Deploying Model. Once it is successfully deployed, you will be able to monitor metrics related to these endpoints in this dashboard. And so that brings us to the end of our demo. Let's look at one of our customers, Alena, and their machine learning journey on Google Cloud. Alena is a smartphone app that leverages proprietary algorithms to drive AI-enabled matches between candidate profiles and employers at a hyperlocal level. In just 3 years, Alena built one of India's leading professional marketplaces on cloud, growing to 22 million users across 70+ cities. With a combination of Cloud SQL, Cloud PubSub, and BigQuery, Alena created a pipeline for millions of daily data points that are ready for Vertex AI to perform ML modeling. The results of running the platform on Google Cloud Managed Infrastructure Services and Vertex AI has been substantial. It is estimated that Alena is compressing the time to build AI models by 20% compared to how long it would take to build from scratch using a traditional data analytics engine. As a result, Alena is able to crunch up to 500 million user interactions every day to power its Vertex AI-enabled algorithms. Thanks to the possibility of rapid ML modeling on Vertex AI, in a situation where fraudsters constantly evolve methodologies, Alena is able to identify and remove up to 60% of inappropriate content on the platform daily. In this session, we learn about MLOps and look at the various tools that are available in Vertex AI that can help us incorporate MLOps practice into our ML systems. We also deep dive into understanding how to run pipelines and manage our models with model monitoring in Vertex AI through a demo. And lastly, we reviewed a customer success story Alena and saw how Google Cloud and Vertex AI helped them automate their ML workflow to build out a successful AI-enabled platform. If you are interested in learning more, please click on the links in the description box below where you will be able to read up more on Vertex AI, check out our AI Simplified YouTube playlist, get hands-on with the platform by trying our step-by-step guided tutorials, and lastly, please reach out and get connected to learn more. That brings us to the end of this video. In the next video, we will go over how you can architect a retail startup with Google Cloud, how can Google power your retail business, and how you can accelerate the retail lifecycle with Google. And that's a wrap. Don't forget to like and subscribe to our YouTube channel, and also to click on the bell icon to be notified whenever a new video is posted.
Hang tight and we'll see you very soon in the next video.